Alright, so we start. So in yesterday's class we had seen the architecture of LSTM, okay, and from now on what I will do is I will, like before, represent LSTMs with this particular box, that is it, okay. Like we were representing RNNs, we will represent LSTMs. Everything that was complex, not complex, is inside this box. What do you get here? AT minus 1, and what you get here is CT minus 1, and your output is CT and output is AD, okay. So this is what an LSTM is. Now you can use all these RNNs to encode what? So let us say you have a big review, okay, and that same ticket kind of example happens. In the first sentence you say something, right, and then you have some 5-10 sentences in between. So for example, you start with the movie was pathetic, and then you say this character did not do that blah 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 full, and then finally you say and hence I did not like the movie. Now movie was talked about only in the first sentence, and between that you have maybe hundreds of words. So if you want to do sentiment analysis on this, how will you do? You would like somehow you should be able to encode this whole review. So if this is your paragraph, you would like to encode this whole paragraph, okay. How will you do it? See, word to vec, what does it do? Encodes every word. Now if you want to encode a whole sentence or a whole paragraph or a whole document, what people did in 2013 when word to vec came out was simply take all the words in the paragraph, okay, use their word to vec embeddings, sum them all, and that becomes the encoding of this. And even that started, whatever was known until then, just this simple thing was working better than all those things. Same you can call document embeddings. Use word to word embeddings for all the words in my document, add them up, whatever comes up is my document embedding, and so on, okay. Now in this case, so that was one way of encoding. What could be another way of encoding that you can do through RNNs? What could be other way of encoding that you can do through RNNs? Yes. What could be one way of representation that you can do through RNN? Simple hai yaar. See, if I pass through this whole review one by one through my RNN or LSTM, the vector that comes last, can I say this represents the whole sentence? There is this my LSTM, I pass the first word through it, right, then second iteration, so all the way until let us say 150th word I passed everyone through this. This final vector that is coming, right, because what are you expecting from this final word? If you want to do sentiment classification, you do it here, right. So you can expect that this particular vector encodes the whole paragraph. Which neural networks will be better, RNNs or LSTMs? LSTMs will be better because they will be also able to capture the long term dependencies. So why you need LSTMs is because there are long term dependencies that are there in, they are there in text, right. You can't really escape long term dependencies in text. and in fact other places too. So for example, if you have rainfall data, you have rainfall data for last 100 years every day, okay, will it follow some pattern? At least if you are talking about in India, this will happen in monsoon, right? But monsoon was some 200-250 days ago. So you do have long term dependencies wherever you have time series data, right? So you will need eventually, sometimes back something has happened that helps me output right now, okay. So all those kind of things, and LSTMs are good at long term dependencies, okay. Now we come to, so you can use LSTM as an encoder. As an encoder of what? As an encoder of the whole sentence, okay. Whole sentence or whole paragraph or whole document, it does not matter. Now I want to do translation. So now I want to do translation. So there are a few questions that nobody asked. So for example, if I have this sentence and let's say you are right, let's say you are learning word embeddings through word2vec. Is it the same word? Word is exactly the same, but here it is noun and here it is adjective, right? So यहाँ पे संज्ञा, यहाँ पे विशेषण, right? So same word, now can the same word embedding represent both? No, these are the limitations of word2vec. So word2vec was a big deal back then, but then you start realizing problems or you start realizing the shortcomings of everything. We will see how to address this. So in today's GPT world, transformer world, you do not have this problem, okay. So just remind me this example when we are talking about transformers, or in fact other examples will also do. Now we start talking about translation. So how will you translate using LSTMs? In fact, I will be good to go if I just remove this. Yes. How do I translate? What was our sentence? No, not this one, the previous one. No, now I can talk about मैं अच्छा हूँ. मैं अच्छा हूँ या नहीं हूँ, but I am talking about it anyway. क्या बोल रहा हो? RCB is pathetic. Now let's say you want to translate this to, so this literally translates to I am good, okay. So now how do we use LSTMs to translate this? Simple question, and you should know it. Now see, the good thing or whatever, translation, because this problem has played a big role in NLP now. This was one of, so these two problems were very hard, translation and summarization, right? They are hard problems, so people were not getting them right. Now translation was the problem that was solved by, I mean that was tried in this paper. Attention is all you need, and we will see what does it mean. But this paper talks only about translation, and then later we will see this was so influential that it is everywhere now, including vision, including speech, vision, NLP, reinforcement learning, not, where not, okay. So if I want to translate this, how should I do it? Quickly tell me. We have talked about this before when we were talking about translation as an example when discussing RNNs. How will I do it? I won't use RNNs anymore. I will use RNNs of the special kind called LSTMs. Now, heard of GRU before? So GRU is a kind of optimization of LSTM. There you have forget and update. Now if you see forget and update, they look similar operations. So GRU clubs them and makes them one gate instead of two gates. Okay. So we are not taking up GRU, people don't talk about that much. Right. So how will I translate? What will be my first thing? So my x1, this is my x1, this is my x2. So I don't need to probably draw this whole thing anymore now. So, and this is my third element. So this is x3 and this is what I care about. Okay. Do I need to output here anything? I am doing translation, I need not output here anything. Okay. So this is my encoder RNN. Okay. This is my encoder LSTM. Now I need to decode. Okay. How will I do it now? Yes. See, why do you call it encoder? Encoder decoder architecture is famous throughout deep learning. If you see UNet, it was a encoder decoder architecture. You encode something, go all the way to the smallest possible features and then scale up again. Translation, encoder decoder. Caption generating, encoder decoder. You encode a image and then decode a caption, right? There are so many things. If you want to do speech to text, first encode speech and then start decoding text, and vice versa as well. So you have encoder here. Now what do I do? This is a very special vector. Why? My encoder is over here, right? So this is a very special vector. I can assume this to be, I don't have a choice, right? This is what I am supposed to do. This red vector, this last vector is encoding the complete sentence, whatever was there in encoder, this encodes the input. Okay. Now what next? What will decoder do? So you start with the start symbol. Right. So you start with the start symbol. What is it you are supposed to, here I expect output at every timestamp. Yes. So this is my y1 hat, and what do I expect? I. Next. So what do I do now? Feed this one back here, and initially what do you do? Initially use teacher forcing so that training is faster. Now this is y2 hat. And then finally this goes in, and what you get is, so this word was supposed to be I, this is supposed to be M, and this is supposed to be good. Finally, am I over? Not yet. I still need to generate N token, right? So this is my translation. Which one to one mapping? See, first of all, if you see, alignment has changed, right? Main acha has now gone to this. So first of all, what will not work is if I literally start translating every word in the encoder, that will not help me. Moreover, I don't have that information. All I have is this vector, and it will be too much for me to expect that this vector has encoded this information as well, that main came before acha and who came after acha. That will be too much to ask for. If it does, good, but we can't take that for granted. All we can hope is this particular vector is encoding the whole thing. It may not, right? So the way things work in deep learning, you hope that this works, write code, train on it, and then prove that this actually works, right? There is no theoretical way of proving things here right now. So you have this, you have generated the output. Okay, once it is AND, your decoder stops generating. Now, what are problems with this? If you are using LSTMs, is it better than using RNNs? Much better, right? So this architecture was in 2014, and this changed NLP like anything, because before that you were doing statistical language translation, and that's a tedious thing to do, right? There are so many rules that, I mean, you guys were not using Google Translator before 2014, right? UPSC did. UPSC did in 2012 or something like that. They used Google Translator to translate English paper to Hindi, and I think they might have used it for others as well. So 2012 or 2011. And steel plant was translated to lohe ka pauda, right? All those, the whole paper had so many discrepancies because translations were mostly rule based by then. There were things called alignments. You have to figure out what is the alignment, right? You might be, NLP people might be knowing about it, right? So here alignment has changed. If you see, acha is second, but here it goes to third. So there are a lot of things that you need to take care of in translation. Now here this is simply end to end. What you need for this to work, what you need for NMT to work, neural machine translation to work, what do you need? And that's a big deal. What you need is a parallel corpus. You need to have exact parallel corpus. First sentence of this should be the first sentence of your translated corpus with proper punctuations, right? So that is a huge need. That's a huge ask, but you have such data sets. So this is fine, and let's say you can train on it. Sorry? That's a, you mean LSTM? Yes, that's a different token. I mean, I'm not going into the difference between token and all these things. So at a gross level, yes, but actually yes. If you, so they did even train for dots and all these for word to vec as well. So if you see that cluster, all these punctuation things, exclamation, dot, comma, colon, semicolon, they are clustered together. But anyway, we are not taking those points right now. We'll take that when transformer comes. Okay. So now question here is, this was a super successful architecture, and in the roots of it lie word to vec, right? Without word to vec, this would be almost impossible to do. So what you input here is word embeddings of the source language. What you output here is, in some sense, word embeddings of the target language, but we do it as a distribution over mod V, right? So all these guys are a distribution over mod V, where your V is the vocabulary size. Now, what's wrong with this? Sorry? Okay, right? So that's a good point. But can I use bidirectional, right? So can I use bidirectional LSTMs? And bidirectional LSTMs will be same as what we did for bidirectional RNNs, right? Replace those boxes with, I mean loudly call those boxes as LSTMs now and not RNNs, right? So I am not even talking about bidirectional LSTMs. So let us say you start using that, but still the problem persists. What is the problem here? There are two problems here, and one problem was in general with text or sequence to sequence. One problem here is you expect too much from this particular vector, right? So we will write this down, encodes the input, but right, too much is expected from this vector. This might be a very long sentence and you want this one particular vector to encode the whole sentence. What was this vector doing here? It was encoding just 2 words. Probably it will do better. But the same size vector you are expecting to encode the whole sentence. It does it better than previous approaches, but now it is time to start thinking ahead. Ki how can I improve it? So that's the first thing. What is the second problem that is inherent to all sequence to sequence problems? They are inherently sequential, right? So I will first process the first timestamp, then second timestamp, then third timestamp. Is there a way of processing 10th timestamp before 5th timestamp or together with 5th? No, you have to do it sequentially. That's why these are sequence to sequence problems. So first timestamp, then second, then third, and so on. Now if you start talking about 2014, 15, 16 and later, people were developing a lot of models. All the papers that we have seen in this, be it VGG, what else we did? LXNet was 2011-12, PESNet, MobileNet, all these things they are around 2014 to 2017, okay, MobileNet was 17, and then YOLO in 2014 late and then 15. So all these papers, fast RCNN, all these things they are of that 3-year period, 2014 to 2017. Computer vision was making a heavy usage of GPU because every image is a independent example. Give it to one GPU, it will take care of one image for example, right? Wouldn't work simply this way, but you can give multiple examples to GPUs and they will work. What happens in case of text? You can give multiple examples, but for that particular example everything is sequential. So you will process the first, then second, then third, then fourth, and similarly in your generation, can I generate this whole thing, I am good full stop, parallelly? एक बार इधर देखो, can I generate I am good this whole thing parallelly? We can't think of it right now, okay? So we can't really make efficient use of GPU. I have lots of GPUs, but the nature of problem is such that I can't make use of it, right? So my processing power, even though I have spent money on it, is not being used. So we need to solve that problem as well. These two problems are super important problems and gives you a reason why transformers were, I mean, they give you the reason for designing transformers. Now, so now we'll talk about attention. So let me just keep this figure, but I'll do this in green. Now, so let's say we have encoded. Okay. Now let's say I've given this start here. I want to output. What should be the output? I. Okay. क्या चीज? Light green works better. Okay. So I. How do I know I should be the output here? See, now what do we do? So let me also draw this third one, because there are only 3, I can afford to do it. So this is मैं अच्छा हूँ, but of course I need embeddings for Hindi words. Okay. Now is this whole thing encoded? I have this whole thing. When I am generating my output, I have this whole thing, right? Now, how do I generate this? If I do it the LSTM way, I take this, apply this, and I hope to get I. What attention does is, right? What attention does is, I'll remove these things. Okay. So now consider this is H1, I am calling it H1, H2, H3. We were calling them until now A1, A2, A3. Okay. Now for decoder network, because these two are different networks, let us say this is S1, S2, S3 and S4. Okay. Now, how do I generate y1 hat? Y1 hat is a function of what? S1? Y1 hat was a function of A1 or not? So it is A1, I am just calling it S1 because it belongs to decoder. I am just calling it H1 because it belongs to encoder. Okay. So y hat depends on S1. Whatever S1 is, that will help me figure out I. What attention says is the following: you take dot product of S1 with H1. This is the dot product. Okay. You take dot product of S1 with H2 and you take dot product of S1 with H3. Done? So now you have a vector. So now you have a vector that I am writing here. I have this vector. Okay. What do I do with this vector? Anything guaranteed on these numbers? No, they can be anything between minus infinity to plus infinity. So what I do? I take softmax. What does it give me? A probability distribution over these three things. Okay. So it gives me a probability distribution over these three things. Let's say probability distribution is this is for मैं let's say this is what it is. It so turns out that in this probability distribution, this is the highest one. What is this whole thing telling me? That when generating output here, right, I should depend maximum on this word called मैं. Okay. So, S1, do this whole math, get probability distribution. Now what do I do last? So how do I make use of this information? So I make a next vector. Do I have these guys? So for notation now let me go there. Their notation is different. Their notation is the same. So what do I do now? What I do now is I have these, so they are calling it E. So they are calling it this as E. Now who are they? These lectures are from Stanford CS224N, which is NLP, right? Why this T here? Right now, so this ET is 1 because we are talking about for the first instance of output, right? Now, I have what they call softmax. So after softmax, it is called, nahi yaar. After softmax, they are calling it alpha. So this thing they are calling E, okay. So this is E1 whatever, but this one they are calling alpha, and alpha T, okay. So in this case this is alpha 1. Is this part clear until now? See, what are we doing? What are we doing? What we are doing is a super simple thing. So first of all, tell me how many of you are not getting what we are doing. Ek baar raise your hands. Flush everything. Even if you were sleeping until now, that's fine. Come back. I have H1, H2, H3 here. What are H1, H2, H3? They are A1, A2, A3s of our good old RNNs. Okay. Why am I calling H here and S here? Because these are two different RNNs with different parameters, so represented differently. I am supposed to take an output here. Am I supposed to take any output here? No. This network is dedicated for encoding the input sentence or whatever. Okay. I am supposed to output here. I have two options. I wholly depend on this particular vector, right? What attention does is it takes opinion from all of them. Which output I am looking for? Output that's a function of S1. So I take dot product of S1 with the first one, second one, third one individually. If there were 30 words here, how many dot products will take place? 30, right? You will take dot product of S1 with everyone. Take softmax and it will give you probability distribution. What do you want from this probability distribution? So once your training is done, you would want that while I am supposed to output here I should make maximum reliance on मैं, because I is a translation of मैं. Okay. Now, So this was just for the first one, S1. I have alpha. What is alpha? What is alpha? If you have understood, tell me what is alpha. I mean, how does it look like? It's a vector of probability distribution over all the encoders. Okay, this is done. Fine. I've got this one. What I do now is I take, so my attention output becomes, that's what we call AT. So my attention AT and T in this case is 1. So that becomes alpha 1 times H1 plus alpha 1 2 times H2 plus alpha 1 3 times H3. See, we are already into transformers, right? Transformers do this thing a bit more properly, but this is what transformers are, right? Because we are already discussing attention, and the title of transformers paper is attention is all you need, and that basically means attention is all you need, recurrence is not needed. So we will get rid of LSTMs, RNNs even for sequence to sequence. Okay, so this is what are the dimensions of AT? What are the dimensions of alpha 1 2, alpha 1 3 and so on? Alphas are scalars, right? They are scalars. What is H1? For us, we have been choosing H to be 100 dimensional until now. So let's keep that 100, 100, 100. So this whole thing makes AT, or in this case A1, a 100 dimensional vector. Okay. So what you do is you get this 100 dimensional vector, and now so you make final prediction on A1 S1. You use this, so your y hat is basically a function of this. Earlier y hat was just a function of S1. Now y hat is a function of A1 and actually y hat 1. And all these superscripts you can put this. Okay. Questions here? And similarly for all these H2s as well, because they belong there. Yes. Questions here? Yes. Alpha 1 and H1. Alpha is a scalar. Alpha 1 is a scalar. Actually alpha 1 is a scalar. Questions here? More questions regarding structure. If you have questions regarding structure, ask them. एग्जाम में अच्छे से, एंड एग्जाम में सीधा सीधा नहीं पूछ रहा हूं मैं. Now tell me what will be A2. This screen is in front of you and you have to tell me what is A2. How will you compute H2, A2? Look at this. What was the rationale behind attention? Take opinion of everybody in the encoder before you generate output at this timestamp of the decoder. So right now we reach where we are done. So we are done generating I, we are here, and this y hat depends on S2. So what will I do? You give me the whole equation now, every step. See this, for alpha 1 you had S1, for alpha 2 you will have S2 dot H1, S2 dot H2, S2 dot H3. That will give you alpha 2 after you take softmax. That gives you probability distribution. Our sentence was, मैं अच्छा हूँ, and we have already generated I and I am supposed to generate M now, right? What do I expect? So maybe it's not a literal translation, but let's say this one is maximum, okay. Now what will happen for alpha 3? S3 dot H1, S3 dot H2, S3 dot H3, softmax. And what do I expect? So maybe this, and maybe here, okay. This solves one of the two problems that we had discussed. What is it? You don't depend on this red vector alone, right? So attention, it basically removes your dependency on just this vector. Now this particular vector is not at all important anymore, because I am, for every output, I am asking everyone in the input, okay. Can it happen that in a probability distribution you get equal weightage on two different words? It can happen, right? Can you translate one phrase to just one word in some other language? So for example, post office, is that one word? So post office, one word or two word, right? But in Spanish it will be, oh okay, oficina de correo, okay. So three words. So in that case what will happen? You won't depend on just one word but multiple words. So when you translate phrases to other phrases, right, in different language, number of words might differ, and in those cases or in other cases too, so this is not a rule that you will always maximally depend on one word. If something depends on multiple words, attention should be able to capture that as well, because you are given information to everything. So this is attention, that's it, I am done. I don't think I will need extra classes. I am left with 4 lectures and transformers will be done. Questions here, by the way? I mean, I've cut down RNN so much that they've given me a lot of time to do this. And once you know transformers, you won't be using RNNs anyway, unless you are a PhD student trying to study whether RNNs can perform better. Yes, questions here. This question is coming in the exam. Yes, यही, हाँ यही अभी करके भी दे देता हूँ मैं. हाँ, sorry, reverse means 3 words, okay. It does not matter, because you start decoding with the start token, you will stop decoding with the end token. So let's say length network decides. No. See, while training you decide. One sentence, then you will have start token, then you will have end token wherever you have full stop or purnviram. So you have trained it such that network now knows where should punctuations come. So once your network is trained, at test time what do we do? At test time we hope it will work as good. So we hope it will work as good. But so see, that's why I did not like this example, because it has only 3. Now if you go to CS224N, here they take a different example. So here they say il a montarte. Now this is a French sentence. So il a montarte, what does it mean is he hit me with a pie. So this montarte, this alone word means hit me with a pie. So there is one word in French that says hit me with a pie. अब पता नहीं वो कितनी बार hit करते हैं pie को कि they just need one word, right? But so il a montarte here is 4 sentence input, and what you output is a 6 word thing. But that same thing again. Yes. Which one? नहीं, मैं क्वेश्चन नहीं समझ पा रहा. हाँ. हाँ. 6. हाँ. नहीं, देखो यहां पे क्या कर रहे हो, योर क्वेश्चन इज एट टेस्ट टाइम, राइट? योर क्वेश्चन इज फॉर टेस्ट टाइम, राइट? कि टेस्ट टाइम पे कैसे. ड्यूरिंग ट्रेनिंग व्हाट हैव यू डन? ड्यूरिंग ट्रेनिंग डू यू थिंक कि हर बार मेरे को n लेंथ का इनपुट और n लेंथ का आउटपुट ही मिला था? Yes or no? During training I must have got all these kind of things. In fact it is rare to see that a same length sentence will get translated to a same length sentence in the target language, right? Most likely they will differ. So in your training, system has seen enough examples where different number of inputs were mapped to different number of outputs. So it might be a hard problem for you to think right now, but system has seen a lot of such examples. So if everything works fine, it should not have problems. Okay, even at test time. More questions? Attention is such a simple idea and it has such a profound impact on NLP. By the way, first attention, if I remember it right, was done for vision. So, yes. Transformer improves this attention and they make it such that you don't even need recurrence. They do everything in parallel. So what transformers do is they don't take language as a sequence, give everything in parallel, but generation has to be sequential. So GPTs, even today, it does not matter which large language model you are talking about, it will generate sequentially, word by word. But it can, but while training, you can do a lot of things parallelly. We'll see that. Astha, Adhiraj, Akshat, Amit, Arohi, Arukshita, Ashmit, Disha, Divyanshu की नहीं है? Okay. ईशान, गर्भ, हिमांशु, कनिष्क, कशिश, केशव, कुशाग्र, मेलिसा, मुस्कान, नीलेश, निहारिका, पारस, पायल, रानी, रिधिका, रिया, रिया सिंह, सौरभ, सृष्टि, श्रेयांश, सिद्धि, सौरभ यादव, स्वास्तिक, वैभव, वृंदा, यश, यशपुरी, अभिनव, अर्चिता, नितिन। More questions here?